thanks everyone for having me. I feel like a little bit of a downer towards the end of the session because everyone's like introducing new breakthrough things, and then I'm saying, oh no, the house is on fire at the same time. So sorry for this, but hopefully we can have a coffee and stuff afterwards and be positive. So maybe the backstory, the context from this is we have a company and we've been building differential privacy tools, and one thing that I would always be concerned about is whether or not we've introduced bugs or issues that mean that ultimately the outputs that we give do not hold to the promises that we set. So they don't achieve the budgets that we expected. So that's kind of what motivated this work in the first place. But realistically, I know everyone says that I tried to keep no formulas here, and I think everyone knows differential privacy at this point. But differential privacy is a formal guarantee, and it's about a bound as opposed to like a qualitative policy. It's about neighboring data sets that change by an individual data subject and what the impact of that data subject can be on the result, and therefore how much statistical noise you need to introduce to minimize to basically make it indistinguishable whether or not the data subject was in the data set or not. We could write out the maths of that, and obviously that is done in many, many papers since 2006. And of course, we can also talk about the policy side of it, which is often introduced in more of a legal and policy settings, like choosing what appropriate budgets should be used for a particular data set, etc. However, both of these things only work if actually you've coded up your implementation correctly. And very often that can be a place where people forget to check, as we found out. So to actually achieve differential privacy in practice, typically speaking, you've got like some data set, some database or something, and then you have some metadata associated with it. Sometimes you derive that from the data, but ultimately, because you want to bound the contribution of a data subject on a result, you have to kind of clean it up. So you do things like you clip values, maybe you need to infer domains. Sometimes you need to make sure that a data subject can only affect a certain number of rows, etc. And ultimately, this allows you to compute sensitivities, which then ultimately allow you to track privacy budgets. And of course, you need to be able to do things like handling nans and edge cases that might come up, like what if there's an infinity in there, etc. So each one of these kind of places, you can easily have introduced a code bug, which ultimately undermines the privacy guarantee of the output. Now, we found this firsthand. So I'm talking about the result at the front, and then I'm talking about maybe the takeaway message we can take from it afterwards. So most of the popular open source frameworks at the moment are very much implemented by the experts who invented a particular algorithm in the first place. And so the tools that we were making, we also wanted to check other frameworks out there and whether or not they had potential issues as well. And we found that a lot of them do. I think the outliers here are pretty much everything done by Google seems to be okay. So congratulations to Google people. OpenDP. And we didn't check Tumult Analytics, but Daniel's in the room. And because it's so similar to OpenDP in how it's developed, I'm pretty sure it's in the safe category. But maybe someone can validate that at some point. But almost all of the other popular frameworks, we found both hilariously simple bugs, which totally changed the privacy guarantee of the result. So I'll just give you a few of these just to get a flavor of it, right? So yeah, in one example, they accidentally they declare, what was it? The sensitivity about new data, but then they actually return the real data in one place. In another place, in working at size of batches, etc., they just use the length of the data set, but it's meant to be in an unbounded DP setting, so you're not meant to have the length. But it's just a very easy coding mistake to make. So these bugs turn up. In other cases, and actually you see this quite a lot, people take the unique classes of an array as opposed to doing this with privacy. So without like thresholding or something, that would actually achieve the privacy that you intended. In other cases, you see, mostly AI, for example, the same budget is like reused multiple times. So they obviously just forgot to compose it, etc. And actually, one thing I didn't write here, but this is a case, especially for a lot of the synthetic data frameworks, is that there's an awful lot of branching in the pre-processing based on the sensitive data in the first place. So if your sensitive data changes, your preconditions of that entire computation change, which is kind of basically leaking some information that's not accounted for in your privacy budget, essentially. Yeah, there's also noise scale collapses. So there was an example where in determining what noise to use, they used the length k, and if that equaled to the number of features, you suddenly had no noise you were applying to things. So it's clear that there's a lot of bugs that were out there in the wild. So if you step back, you can say, well, why is this the case? And there's been loads of attempts, like over the last 2 decades, literally 2026, to build rigorous ways to derive differential privacy frameworks that would be more secure. So one thing that was quite popular, maybe, I don't know, 10 years ago or something, was the kind of formal DSLs. There was like pink, etc. These are strong, but they pretty much required you to rewrite your whole systems. And that wasn't a huge runner. I would still claim that OpenDP and some of the other frameworks probably look like a DSL because they might have a Python interface, but you're like chaining together things in quite a non-Python way. The second approach is black box auditing. So this is just really slow. So basically, you're creating lots of samples and passing it through the system, and you're working out the empirical distributions of what it creates, and you're comparing that to what you would expect for a particular privacy budget, and you're saying, yeah, it looks safe or not, at least within some some kind of margin of error. And finally, you have unit tests. And everyone who's a software developer here has written unit tests and integration tests on almost everything, but they're not really designed, at least until now, for privacy mechanisms. So people were they were very rarely actually like checking the mechanisms and the piping to get to those mechanisms. So we were trying to find a way that we could, well, or how we found all of the previous bugs that would just be simple, reproducible for our own internal teams, and then hopefully useful more broadly externally. So what we did was we just kept it like as simple as you can, like KISS, keep it simple, stupid, like 100% here. So for any framework, you can kind of think of it in terms of a number of steps, and some of these steps might repeat. So you have an input, then you pre-process the input, you apply a privacy mechanism, you post-process it, you have some output. You might have chains of this. So like, for example, in synthetic data, if you look at the MST algorithm, for example, you would take like one access, compute a histogram, do that for each access of the data, and then look at pairs and use the exponential mechanism to choose good pairs, et cetera. So you're taking the outputs of one step and feeding that as a kind of an input to the next step. But it pretty much creates these chains. And what we found was if you were like reasonably sensible, and you weren't using like NumPy for your noise or something like that, but let's say you were using, we used OpenDP for the mechanisms that we use. The chances were that step 3 was actually reasonably safe. But where most of the bugs were in kind of pre-processing steps before the mechanisms. So what you thought was your sensitivity was just incorrect. And so our approach was just super simple. All you would do is you would go to your favorite framework, you would find the privacy mechanism, and you just wrap it. So you wrap it for your unit tests. And this sounds so ridiculous when I'm saying it to an audience, but it's just incredibly effective. So you wrap it, and all you do is you just run it with the data set, and then you run it with the data set again with that extra record introduced or removed, and you just look at the difference on the inputs coming in versus what the sensitivity was that was declared, and you catch like bugs in everything, it appears. So that's the first step that we did. And then obviously you have this propagation. So if we were to actually apply the privacy mechanism, we would be adding 2 different random numbers. So that could produce kind of like a fork in the road. So what we would do instead is we would record the result that came out of the first mechanism, and then replay it in the second run for the data set as well. So yeah, first we recorded, and then we replayed it. That allowed us to propagate it across like every step in, for example, MST, et cetera. And so you could identify if there was an error, not in your first privacy mechanism, but in a dependent one that happened further upstream. And finally, for the privacy mechanisms themselves, so like some of the frameworks were pretty rigorous. Like using OpenDP as your mechanism was like fairly robust, but some people like handwrote theirs or whatever, and it could be a black box thing that you want to test. And so if we do the black box audits just on the mechanism itself, that's typically speaking quite low dimensional and is really isolated. So you can do this super fast and get good empirical checks to ensure that, yes, the mechanism is reasonable and correct. What went into it is reasonable and correct. What came out of it and propagated forward changed together and was reasonable and correct the whole way through. So the steps through it was run the program on a data set, record the primitive calls, inputs, outputs, parameters, the RNG state, replay it for a neighboring data set, force the mechanisms to return the same outputs from phase 1 to phase 2, and then check for invariance and sensitivities. And as you can imagine, this makes like a very simple like PyTest framework in Python that you can just apply to your frameworks. And you don't have to. We were able to get all of those results in like 2 or 3 days between myself and Shooter and like 1 or 2 others. So it was not like a big chunk of work by any stretch. Oh, by the way, we've definitely found issues with our own code that we've solved. So I'm not pointing the finger at everyone. This is kind of a community thing, I would say. OK, so from privacy violation to bring it to like a debug failure. So we can identify things like a parameter changed, this mechanism call disappeared, this input moved further than the declared sensitivity, this component spent more budget than it reported, and so on and so forth. And actually, very often, it doesn't identify like the line of code where the bug arrived from, but it reduces it to like, it kind of sandwiches it from where inputs arrived to where they were used. So that meant, for example, in the JAM, Ryan McKenna's framework, they brought in JAM, and the original source code in the paper was correct, and then when it was ported in, like a factor 2 was made into a 4, which then made the sensitivity incorrect. But it wouldn't give you that line, but you knew roughly where it was, so you could quite easily like identify it manually. So it like narrowed the space quite a lot. Yeah, so yeah, the same thing as when the account is untrusted. We're able to isolate the mechanisms, sample, estimate, and then compose cleanly, as I previously said. So I think the reason we're trying to kind of bring this to people's attention is very much from like a public service announcement more than blame. Even though the space of pets is increasing and moving very quickly in the right direction, there's still gaps that need to be resolved along the way. Like obviously, if you were to compare differential privacy or secure multi-party computation or homomorphic encryption or any of these things to like a FIPS 140-3 certified boring algorithm that's in everything, there's just a maturity gap. And so I think it's really important for the community to try to like reduce these gaps so that these technologies can be used in practice more widely. Yeah. So one thing to really just mention is that passing the tests don't prove correctness. It's more almost like a smell test. Like it'll catch something if it's obviously wrong, but it's not there to prove correctness. And it takes a fairly simplified, like we called it gray box, because you don't really need to understand the entire code base. You just need to be able to isolate where the mechanisms are applied. And we found that this caught a number of bugs and issues. There are other approaches that we've been looking into, but we've kind of used them internally. We haven't like released anything yet. So some approaches were trying to use static analysis to ensure, so like taint analysis that you use for security checks to look at the flow of data to ensure that like your metadata came from the original metadata, for example, or the data went from the original, like there was no branching based on the original data, et cetera, et cetera. There was no way that data could have gotten to the end without going through the sanitizer, which was the mechanism, et cetera. That is not in this repository. This repository is online. It's called the DP recorder. And the other area that we've seen a fair amount is that because of the statistical tests, it doesn't check things like floating point issues. So in a lot of frameworks, they'll just use like NumPy or something, and then use the Laplace, or in I think JAX as well. Actually, they use the inverse error function, which makes it easily like reversible. Now, not an issue in JAX because you're like mushing them together over like many steps of like some big algorithm. But if you were just to use it like in isolation, these are things that like we wouldn't be able to catch using these frameworks. But it's a good way to catch a lot of things very quickly and simply. Yeah. So the takeaways. I think if you can just remember one thing, I would just say, just test your code. That's just like the basic one. Yeah, so thank you. We can leave it there, I guess. If there's any questions, I'll be happy to answer them. And maybe the last thing I wanted to say is this was joint work. So Tudor and Oriane are in INRIA. Damien and Daniel, I guess many of you know. Daniel's there. And David Erb, who was an intern at the time with us, but has been fantastic. So joint work. So thank you to all of those people too.